Greetings, everybody. Welcome to the latest edition of the Physics Corner with your host, Dr. Christopher Sorolla. Today we're talking about inductors and how they can be used as electromagnets. So, for starters, an inductor is a fancy word for a coil of wire. If you see something that looks like this, besides just being a coil of wire, that's also the circuit symbol for an inductor. And we'll be dealing with inductors within AC circuits at some other video. But today we're just taking a look at the coil itself and what happens when you send some current through it. So let's get started. Let's imagine we have a coil that has 1,000 turns, obviously not this picture here, but 1,000 turns, has a length of 10 centimeters. Now by length specifically, I mean from one end to the other like this. One thing that used to confuse me when I was a student was I thought, oh, you'd have to unwind the entire coil and talk about that as a total length. No, that's not what's meant. What's meant is simply from one end of the coil to the other like that, okay? So that's 10 centimeters. And then the radius of 2 centimeters. And that, by the way, takes care of what I was worried about way back when. 2 centimeters is the radius of these circles. Now, it's drawn at an angle so they don't look like circles, but of course, if we were to tilt the coil in the correct orientation to us, yes, it's a circular coil. And again, as we've talked about in some other videos, circles are the most common type of shape of a coil that you have. It's not the only shape you can have or do have, but it's the most common and we tend to stick with it. All right, so let's imagine we have that as a setup, and then we connect this to a power supply and end up having a current of 5 amps going through the coil. Now, by the way, in this particular example, we can make this a DC power supply, in other words, direct current. We'll talk about AC circuits in other videos, but this can be imagined to be a DC circuit. And what that does, basically, as the current, as you will, travels into the coil, you can imagine current coming in this direction, and then it makes loops to go along with the wires, right? And then, of course, comes back out the other end. Now, the current or the magnetic field around the wires that are straight, the straight parts, that's a different question. Again, not something we're talking about today. But when that happens, you end up creating a magnetic field inside the coil. The magnetic field will be going straight through the middle of the coil, and at the very center has a particularly constant value. So a coil of wire like this with a constant amount of current flowing through it is a magnetic equivalent of a parallel plate capacitor and its ability to work with electricity. So if you recall in previous videos or previous discussions in your classes, a parallel plate capacitor is a device which we can set up to use or to create a constant electric field in between the plates. Well, magnetism uses moving charges or current, so instead of having stationary charges on opposite sides of plates, we need to have a way to have current flowing. But if we have current flowing through a nice commonly smooth coil like this, then we can set up a constant magnetic field. And it also knows in that inside the coil, mind you, now outside the coil it's a different story, but inside the coil, a magnetic field is pointing in a constant direction and will have a constant value at the very center of the coil. So this is the magnetic equivalent of parallel plate capacitors. So that's another reason to talk about this. Okay, so first things first, what is the inductance of the coil? Then we'll ask what's the magnetic field inside the coil. And since we've talked about it, how much magnetic energy is stored in the coil when we do this. Let's get started. So, first part, let's look up the formula for inductance. Now, inductance has the symbol capital L in physics. Yes, we realize that inductance starts with an I. This is an L for different reasons. It's actually named after a scientist, a physicist, if you will, back in the late 1800s. So, the formula is mu naught n squared A over little l. Now, that is for a cylindrical coil of wire like we have here. And what do each of these parts stand for? Well, we've already encountered a few of these in different videos. Capital N is the number of turns, and in this example, it's 1,000. Capital A is the cross-sectional area. This is the area of a circle. We'll calculate that soon enough. Little l here is the length. And so, as we were sort of indicating before, from one end to the other coil is the length. That's the little L we're talking about there. And then there's mu naught. What's mu naught? Well, this is magnetism. And so when we talked about electricity, we had something called the permittivity of free space. And one way to sort of envision that was it was the ability of free space or vacuum, if you will, to permit the electric field to go through it. And the smaller that number was, the easier it is for the electric fields to travel through it, and electric fields travel through empty space or vacuum better than anything else. Well, there's an equivalent for magnetism. Okay, magnetism is called the permeability of free space and has basically the same sort of connotation, how easy it is for magnetic fields to travel through vacuum or free space. And that particular number is here, 4 pi times 10 to the minus 7th in standard units. And the standard units for mu naught, or the permeability, is Teslas multiplied by meters divided by amperes. So that's where that comes from. Now, just like you also did or could do with, say, parallel plate capacitors, you could take, for example, a dielectric or insulated material, place it between the plates, and change the capacitance of the parallel plates. You could, say, take a material, put it inside the coil, and thereby change the strength of the magnetic field in the coil. That's an idea you can do. There's an equivalent way of talking about that. We're not going to worry about that today. So that's a different discussion for some other time, perhaps. So let's calculate the inductance. So mu naught, 4 pi times 10 to the negative 7th, and then Tesla meters per amps for its units. By the way, this capital A for amperes, that capital A represents area, so let's not get them confused. Capital N is our 1,000 turns of wire. What is capital A for area anyway? This is a circle, so it's pi r squared, right? I'll write that off to the side so it's obvious what I'm up to, but that's what it is, okay? Just to remind everybody what we've got, okay? And so if I put that in, and I've already gone ahead and calculated it, capital A then is 1.26 times 10 to the minus 3rd meters squared. If you want to, wouldn't be a bad idea, double check my math, make sure I got that number correct. Okay, all of this divided by the length, again from here to here, which is 10 centimeters or 0.010 meters, like that. Okay, so grind these numbers out, and the inductance is 0.0158 henries, or you'll sometimes see people record this in millihenries, and that would be 15.8 millihenries, like that. We'll stick with this number today, but you can sometimes see it that way. The reason to bring this up, just very quickly, a henry is a decent size unit, and 1 henry is a lot of inductance, and it's not terribly uncommon to see a lot of inductors that one would work with have values in the millihenry range. So that's the only reason to maybe say it that way. Also, units are called henries, okay? What is a henry? A henry, of course, well, you can do that for yourself by seeing all the units that go into playing this out. But it's the unit of inductance. Just like, for example, the farad was the unit of capacitance, right? Remember, the capacitance idea was the capacity or capability, if you will, to store electricity. The henry represents the unit of the capacity or ability to store magnetism. It's a very similar sort of notion. The one thing that's obviously very different, it's current or moving charges instead of stationary charges as it was for the capacitor situation. But again, we're getting away from our task today. So on to the next part. What is the magnetic field? Now, I'm going to go ahead and write the formula for magnetic field that you would get if you looked it up, and for a coil wire like this, or if you were to look it up, you would often find it called a solenoid, and that's just a different name for the coil wire. It really doesn't matter for otherwise for our purposes, but you might encounter that. But I want to do something a little bit different, and I'm going to leave this as a task for you folks if you want to try to show it for yourselves, that you could take this formula and rewrite it in terms of the inductance. And if you were to do that, you would come up with this as your formula. So for a coil of wire, or an inductor like we've got drawn here, the magnetic field strength inside the coil, and again, have to emphasize this is inside the coil, will be this, interestingly enough. All right, since we've got this result, let's go ahead and put in some numbers. So 0.0158 henries, that's why I'm using this value, keep it standard. The current was 5 amps. By the way, notice that the inductance didn't require us to find out what the current is or to use the current in any fashion. Inductance is a geometric idea. It depends upon the geometry like the cross-sectional area and the length, and the number of turns of wire, and it depends upon this magnetic constant, this permeability constant. It's very similar in a fashion, again, to how capacitors work, right? Capacitors also depended upon a cross-sectional area and a distance and a constant, electric constant in that case, and so on and so forth. So they're comparable ideas. All right, divide by the number of turns, which is 1,000. Our area we calculated before, or I argued for before, and I let you calculate, to be quite honest. It looks like that. And when this is calculated, we get 0.0628 Teslas. And again, if you would prefer to put it into, say, milliteslas, that would not be unreasonable to do that. You can sketch it like that. Okay. Last thing, let's go ahead and talk about the amount of energy stored by the inductor. And again, there's a very similar comparison between this and energy stored by capacitors. So for capacitor, the potential electric energy was 1/2 CV squared. 1/2 multiplied by the capacitance multiplied by the voltage or potential difference squared, right? In the case of an inductor, the potential energy, specifically magnetic potential energy, and that's why there's a B as a subscript, because that stands for magnetism, right, is 1/2 Li squared. So notice what's happening. It's the same format. And by the way, another quick aside before we calculate, this is very common in physics. To calculate an energy of something is often a 1/2 multiplied by some constant number or feature multiplied by some variable squared. So for example, kinetic energy, 1/2 mv squared, right? The mass of an object multiplied by the speed squared. When we talked about, say, spring potential, it was 1/2 kx squared. 1/2 multiplied by a spring constant, literally a spring constant, and an x being a distance, which is a variable idea, squared, and so on and so forth. So when you're studying and you're trying to figure out or remember, say, a formula for an energy, not always, but there's a very good chance it's in this sort of format. 1/2 multiplied by some constant multiplied by some variable squared. And in this case, the current is our variable, the thing we can change. All right, let's put in these numbers for this particular example to see how it works. So again, 0.0158 henries. We were told, again, 5 amps for the current. That is squared, mind you, right? And then my final answer is 0.198 joules. And if you were to round off just to get an appreciation for it, to say it's 0.2 of a joule, I wouldn't get too worried about that. So that's what this is capable of. So you've talked or seen in many other places by this point how much a joule is worth. So I'll leave that for you to sort of contemplate. But this is a very good presentation then of, first of all, an inductor. Second, I talked a lot about relating it to what a capacitor looks like. And of course, as we always do, we show you the math, right? We try to get numerical examples and show you how you would actually calculate these things. So there we have it, the inductance, magnetic field of an inductor with a particular current flowing through its wires, and due to that, the amount of magnetic potential energy stored by this coil of wire. So technical assistance, as always, is from Sidney Gauchaw and Sophia Turner. The University of Mississippi and University of Southern Mississippi supply funding for these programs. I am your host, Dr. Christopher Cirola, broadcasting from Hattiesburg, Mississippi, saying thank you very much for your attention and clear skies.